Hello, all the precious of this planet. My name is Krishnakant Bhosale, 15-year-old aspiring rocket scientist. I have designed an inexpensive, lightweight rocket for the DRDC. Methodology for it was to choose a correct material. Now I am going to tell the material of each and every component and the reason behind that material. So let's get started with the nose cone. The nose cone is the part which experiences a very high aerodynamic drag. So I have made a nose cone with a polystyrene which have very low amount of density and have a high strength. The shape of my nose cone is ogive with and my length of my nose cone is 20 centimeter with the base diameter of 5.8, and I have polished my nose cone thus it will experience a less aerodynamic drag. So moving forward to the body tube, the material of a body tube can affect the entire rocket. That material's weight can affect the weight of the entire rocket. So by keeping this in the mind, I have made a body tube using cardboard which have very low amount of density and have high rigidity. And the length of my body tube is 41 centimeter with the outer diameter of 5.84 centimeter and the inner diameter of 5.44 centimeter with the wall thickness of 0.2. And the component finish of this body tube is polished, thus it will face a very low amount of aerodynamic drag. So moving to the fins of a rocket. So the fins plays a very important role for the stability of a rocket. It allows rocket to move in a correct trajectory. So I have made my fins using a balsa wood which have a very low amount of density, thus making my fins very lightweighted, and it have a very high considerable amount of strength, and the component finish is polished. And these are the dimension of my fins, and the fin cross section area is airfoil. The airfoil shape can reduce the aerodynamic drag on the fin. So moving to the static margin. So stability of my rocket is up to 1.76 caliber, and the center of gravity location from the tip of the cord is 45.3 centimeter. So moving to the practicality. So while designing this rocket, I faced two big challenges. That first challenge is to make a rocket stable, and because if our rocket is not stable, then it will not go in required path, and I overcome it by designing a fins in such way that increases height and the stability of a rocket. I focused on the sweep length of a fin which is directly proportional to the stability and the altitude achieved by the rocket, and the fin cross section area also plays a very important role for increasing the stability of the rocket. The second challenge which I faced was to achieving a maximum altitude. For getting a maximum height, I made my rocket shorter and narrower so that it can cut the flow of air easily and can give its maximum performance. Here the component finish also played a very important role. I kept my component polished, because of which my rocket overall experienced a very less aerodynamic drag. And the most important part of a rocket is the rocket motor. I have used three motor of a G class in which each has total impulse of 82.9 newton second and average thrust of 93.1 newton, and have a launch mass of 4.78 ounce and empty mass of 3.34 ounce. And the total propellant carried by the three clustered motor of a G class is 4.32 ounce, which gives the total impulse of 249 newton per second. My rocket uses a parachute recovery system, and my parachute have a diameter of 103 centimeter, and it have a 6 line. Each line is having a length of 40 centimeter, and it will be deployed at the apogee. Moving to the performance of a rocket, my rocket has achieved an altitude of 1422 meter with a maximum velocity of 264 meter per second. With the parachute recovery system, my rocket ground hit velocity is 4.15 meter per second, and it took 15 seconds to go up to the apogee. If we plot flight side profile graph, then we can see that this was the point at where the motor was totally burned out, and that was the point of apogee recovery device deployment, and it was and this point was a ground hit. And this is my stability versus time graph of my rocket. As you can see that this was the phase where my motor was totally burned out, and this was all about the graph. Let's took the 3D unfinished look of my rocket. So this is 3D unfinished look of my rocket. and this is a side view of my rocket. And let's change the view type. So let's take a back view of my rocket. So this is a black view of my rocket, and this is again a 3D view of my rocket. Let's see my rocket through Photo Studio. So this is the rocket demonstration. So at last I wanted to thank Helium Learning Labs and SDNX to providing me a great opportunity to be a part of DRDC. Thank you.